Hey YouTube, Booth Dog here. Another week of learning and teaching like this. Hope we're kind of getting used to it. I'm definitely settled into a routine. Just want to remind you that I'm getting a lot of great questions from your exit tickets each day. Please remember that I do try to answer those in the next day's Google Meet. So if you want answers to those questions, please, I know it's not always possible, but try to join that Google Meet. And if you have a question you need a desperate answer to, then email me just to make sure that I get an answer to you, okay? Before we jump into today's lesson, we do have another promotion today. Today's video is sponsored by Paper, okay? Yes, real paper. I'm a firm believer in doing math on paper, of course, with wooden pencils, not that mechanical trash. Anyway, let's turn things over to Mr. Boothman, and let's get started. Happy Monday. Some announcements to start our week, okay? Today's exit ticket will ask you to submit any questions you might have from Unit 8. So this is going back to before break, 8.1, 8.2, and of course 8.3. This is due by midnight tonight. Your Unit 8 exam will be this Wednesday, so we will review today and tomorrow. Additionally, just to clarify, there is no unit tracker for this unit. You don't have to submit a unit tracker here. Just follow along with the review, do some practice problems today and tomorrow. All right, what I'd like to do today is kind of just summarize the unit as we go along. So I'll summarize all of the main concepts that we've studied. I have posted some practice problems along with an answer key. So I ask that you work on that today and tomorrow as well. Tomorrow in this video lesson, I'll go through some of those problems. But really today I want to summarize some concepts, hopefully clarify a few things, and let you do as much practice as you can. Okay. Again, this is a real grade, your unit exam. Take this seriously and put in as much effort as you know you should. So looking back at 8.1, 8.1 was all about accumulated change. Okay, so Unit 8 as a whole was applications of integration. 8.1 looked at specifically word problems and how this accumulation of change allows us to answer a bunch of different questions for real-world scenarios. So the main formula, the main concept from that section was that our final amount is our initial amount plus change, okay? Another word for change, if we're talking about velocity, displacement, okay? In general, that's the integral of whatever rate we are given. So final equals initial plus change. Displacement, so again, if we're talking about velocity, displacement can be negative. So displacement is basically my change in position. Okay? If I started here and I move here, that's a positive displacement. It's in the positive direction. If I start here and move here, that's a negative displacement because it's in the negative direction. Now there is a distinction between displacement and total distance traveled, because if I move from here to here, I still traveled some distance. So that is the absolute value of our displacement. Okay. And displacement, of course, that change in position is just going to be the integral of our rate. In this case, our rate is velocity. So we're taking the integral of velocity to get back to our position. Okay. 8.2 was all about area between curves. So this was a pretty straightforward equation. We have the integral of whatever our top function is minus our bottom function. Okay, so subtracting that will give us that actual area, that distance between those two curves, and then we're taking an infinite sum, giving us the area. To find our limits of integration, sometimes they're given to us, sometimes they're not. Usually, okay, if we have two curves here, we need to consider where those curves are intersecting to actually find those limits. And to find our points of intersection, we of course set our functions equal to each other and solve for our variable. Okay, so 8.2, pretty straightforward. I don't remember us having any main issues there. And of course, that led us directly into section 8.3. I know this is a little small. I'll make sure to post this PowerPoint as well. So 8.3 was all about volumes of solids. So volume is just the integral of the area of a cross-section of our shape. If we take an infinite number of those areas of cross-sections, add them together, we should get our full volume. Cross-sections, we started by talking about what happens when they're known shapes, they're basic shapes like triangles or squares or circles. Okay, so that's given some base, and then we're told that the cross sections are some certain shape. Okay, so we find the area of the cross section and integrate it with our limits of integration. From there, we moved on to talk about solids of revolution. So what happens if we take an area, some region, and we revolve it about a line? Okay, so we only talked about revolving these areas around horizontal or vertical lines. If we revolve about a horizontal line, including the x-axis, then we're integrating with respect to x. If we're revolving about a vertical line, including the y-axis, we realized it's much easier to visualize these cross sections in terms of y, so we will integrate with respect to y. In general, for our solids of revolution, our cross sections are one of two things. Either they are a solid circle, and we realize this by drawing our picture and trying to get a good visualization of what's going on. If they are a solid circle, then the area of our cross section is simply pi r squared. Sometimes it's not a solid circle, there's a gap in the middle because we're revolving around a line that's kind of far away. In that case, a cross section looks like a washer. In such a case, the area of our cross section is pi times, we have big R squared minus little r squared, right? We're taking our large circle's area and we're subtracting away the smaller circle's area because that's the gap in the center. And that leaves us with the actual piece in the shape. Okay, so radius, whether we're talking about a solid circle or our washer, these radii are always given by function minus axis. Okay, now if we're just finding that actual distance, sometimes that actually would involve adding the axis. But if you're struggling to visualize that sometimes, since we're squaring our radius in all of these equations, function minus axis works every single time. Okay? Now, when we're talking about a washer, of course, we have two radii to consider. Big R, capital R, involves the furthest function from the axis of revolution. Okay, so if you're standing on the axis of revolution, which function is furthest away? That's going to be big R, or big R is that function minus the axis of revolution. Little r involves the closest function to our axis of revolution. That was all that we studied in Unit 8. Most of these ideas are interrelated. 8.1 was kind of different, looking at word problems, but 8.2 and 8.3 were really just visualizing these shapes. We're dealing with finding these points of intersection and so on. You guys have been doing very, very well, so please keep it up. Work through those practice problems. Check your answers with the answer key that I posted. We'll go through some of these in tomorrow's lesson. Please complete your exit ticket by midnight tonight. Practice, practice, practice. Come to our Google Meet, reach out to me. Please keep up your good work. Many, many of you are just incredibly impressive to me that you're still succeeding despite this craziness that we're experiencing right now. Please, please, please continue to hold those high standards for yourself because I certainly am as well. All right, see you tomorrow.
Thanks, Boothman. What a great guy. Please make sure to reach out to me with any questions you might have. Otherwise, I'll see you tomorrow.